It's my first time at CppCon. I've thought about going for a lot of years and now kind of regretting that I didn't go sooner.
A little bit of a warning about this talk. There's going to be a lot of code, and some of it's going to be a lot on screen at once. So I try to make it as readable as possible. Sometimes the font size is going to dip a little bit below what I would be comfortable with. So if you are sitting towards the back of the room, especially those really small people right at the back, you might want to consider coming forwards a bit. We have the big room, and we've got a big crowd here today. For those watching on YouTube, it's about the size of a football field, and it's completely packed, at least with chairs, and quite a few people as well. So yeah, do consider coming forwards, especially if you've struggled to read the code, because every slide is going to have a lot of code on, just to warn you now. So given that it is going to be mostly code, just to make it a bit more visually interesting, I also asked ChatGPT to generate me a whole series of robots that are going to help guide us through the code. So watch for those, including this one. I particularly like how this one came out on the title slide. So I'm Phil Nash. I am now an independent consultant, trainer, conference organizer. And on the subject of training, that's now my main source of income. So if you have any training needs, especially test-driven development, coroutines, or effective C++, do come and see me. Be here till Friday morning, or you can reach me on Discord, or watch for me next year, next CppCon, for my class. But enough about me. Topic today, modern C++ error handling. And I chose this name very deliberately, because this is not the first time I've done a talk on error handling. Back in 2018, I did optional is not a failure, and 2019, the next year, followed up with the dawn of a new era. And while I still stand by these talks, in some ways they're a bit dated now, ironically, because they're a bit too forward-looking. Not quite so much the first one, which started off with a bit of a review of existing error handling techniques. And we're going to do a bit of that again now with a bit of a fresh take. But towards the end, we built up to what we could do in the future, finally introducing Herb Sutter's P0709, his value-based exceptions paper, sometimes called static exceptions, which hasn't really gone anywhere in the meantime. So maybe that was a bit of a dead end. Unfortunately, the second talk really dug deep into that one. So a little bit more of a dead end. But that one did at least touch on stood optional, stood expected for error handling, and the Monadic Operations, which at the time were still off in the future, will accept stood optional. Now they're actually in C++23, so we're definitely going to look at those today, have a fresh take on them. They're slightly different to what I talked about before, and we're also going to dig into them a bit more. And as well as language features, I'm also going to look at some of my own ideas about effective error handling and how we can merge some of these things together. And I'm going to talk about one feature that's still coming. Just towards the end, we will touch on contracts a bit. It's not going to be a deep talk on contracts. You should have seen Timo Dumler's talk earlier today on that. Lisa Lippincott has one tomorrow, a bit more of the philosophy. But I'm going to talk about how it fits in with the other error handling techniques and how to make sense of it all. So that's what we're going to do, and we're going to do it in two parts. The first part, we're going to talk about what I'm going to call disappointments, which is a term coined a few years ago to talk about any type of error condition that is predictable, something you expect, you just don't necessarily want. You're disappointed if it happens, but you can work around it, you can go on, and you know what to expect. So that's a disappointment. And that covers pretty much all forms of control flow error handling, as well as exceptions, as we'll see. They all come under this umbrella. That's going to be the first half. And then in the second half, we're going to talk about things that are more logic errors, often bugs in the code, things that you can't really predict, you don't really know what state you're in. And that are really more the domain of contracts, both conceptually and finally the language feature. And we'll see how that fits in. And the total on this slide here is a bit of a play on words, because it turns out that if you use disappointments for your error handling, you will generally end up with a total function. All possible inputs have a valid output, even if some of those might be represented as an error. Whereas a partial function is one that's only valid for certain inputs. And that's what a narrow contract will give you. We'll come on to that later. Let's get started. So for this first half, we're going to be using one particular code example. So I hope that's readable. Going to be an evolution of this as we go through, but it's going to be the same basic idea. We're just parsing a string into an integer. Nice and simple, so we can focus on the error handling. And we're going to use this implementation. Nothing complex, it's oversimplified for the purpose of this slideware, but it serves the purpose. So that there's some extra things you might want to do. What you can see there, hopefully, is that there's two exit points. And only the last one will give you a fully parsed integer. But there's no error handling here. So if we were to call that with different inputs, like this, different strings, we will get different outputs. Now I've used std println here, that cpplusplus23. Don't let that distract you. Obviously that's just for printing the result. You could use cout or printf or whatever. I'm trying to be modern where I can. So if we give it a string that is fully an integer, then it will, of course, convert that faithfully to an integer. If you give it something that's followed by some non-numeric digits, it's still going to give you an integer, because if you can see in the implementation, it just stops parsing at that point and returns what it's got so far, which is incidentally what IOStreams does as well if you use that for string parsing. So it should be familiar. And finally, if we start with a non-numeric digit, then we get 0, because that was what we started our accumulator with, and we never got any further. Again, that's what IOStreams give you. And that actually might be a valid approach. In some cases, just giving a best effort and carrying on regardless is the right thing to do. But very often, we're going to want to distinguish these error conditions and take appropriate action. So that's what we'll do next. Now, the problem with this, and it's very often the case, because this is computing something for you and returning a result, we can't use the return value to signal the error, at least not in a straightforward way. So sticking with old school approaches, one thing we could do is just have a separate function that just parses the integer just enough to see whether it actually, parses the string to see whether it is an integer or not. And then it can return a boolean result. And you can write some test code that will just make a call to that. And I haven't written it here, but could then follow on with a call to parse it. That's a valid approach. It might not look like the best approach here. In some cases, it's perfectly valid. In fact, we're going to look at something like this a bit later in a different context. But it does work. One other problem with this is we're not distinguishing between the case where we're starting with numeric digits or where we're starting with non-numeric digits. And that may be important as well. The Boolean only gives us, obviously, the two results. So we may introduce some sort of error code, an enum, an integer, whatever it is. An enum's a good choice. So now we can distinguish between three states. And the code gets a little bit more complex, but still pretty straightforward. Hopefully no surprises just yet. The usage code will still switch over that, and we can get the expected results. Now we've got three different possibilities. And notice now the implementation code is not really making a judgment about whether it's an error or not. It's actually leaving it to the calling code to make that judgment. So the starts with it may not actually be an error in your case. So that is a common pattern we're going to look at, trying to defer the decision of how to interpret and handle the error to the calling code. All right, but obviously there's a lot of duplicated code here and duplicated effort. So this is probably not what you want to do with a string parsing function. So again, keeping to older techniques, we might use what we call an out parameter. In this case, we take this integer by reference, and we're going to use that as the accumulator, and finally return in this case, it's going to be the enum to tell us the parsing status, and the result is in the argument that you pass in. Sure, we've all used techniques like this before as well, and that works. So we've removed the duplication, we can signal different errors, and everything's good. Except it's a little bit ugly, doesn't compose very well, doesn't feel very modern. So now we get to, one other one other approach it's worth mentioning. Not necessarily recommending you do this. Some of the other techniques, older techniques I do, but setting a global variable or a thread local variable with the error state is something that I'm sure we've done. Erroneous is the conventional way to do that. But I wouldn't do it this way, because Erroneous is really for distinguishing different types of errors, not for signaling it in the first place. You probably want to return a boolean, and that puts us back into the same problem we had at the start. But I mention it here because there is one other technique which I'm not really going to discuss today because it's a third-party library, but if you've seen Boost Leaf, under the hood, this is sort of what it does. Sets the error status into a global or thread local variable, but then gives you more of an exception-like propagation. So you get a bit of the best of both worlds. So that could be worth looking at. But I'm not going to dig into that today. Okay, so exceptions, the elephant in the room. We've had them since, I think, around the turn of the 90s, maybe even earlier. Can't really argue they're modern C++ anymore, but they are still, fundamentally, the default error handling approach in C++. And with good reason. They tick a lot of boxes. They are very low impact on the happy path, probably no impact at all, performance-wise. They shuffle all the error handling off to a separate section at the end, so it cleans up the happy path. But they do have some downsides as well, to the point that, according to one developer survey a few years ago, and I haven't checked the updated statistics, but at the time, about 50% of those surveyed said they couldn't use exceptions in all or part of projects they were working on. That's quite a sobering statistic, that the primary error handling mechanism in C++ can't be used by basically half of the community, according to that metric, or certainly a sizable proportion of it. And there may be valid reasons for that. In particular, the non-determinism for sort of low latency systems, the overhead on the error path if you're expecting lots of errors, not just exceptional cases. So we do need to look at other error handling opportunities. We've looked at some already, but it was worth mentioning exceptions. So far we haven't been particularly modern. Let's at least bring it up to C++ 17. I think a lot of people are still on C++ 17 or have recently moved on from it. This is still fairly new. Still optional. Sure, you're familiar now with still optional, but let's just review how we would use that. So now we can combine that Boolean result and the actual result we wanted in our return type. So we have an optional int, which can either hold the value we wanted, or we have an empty optional. And in the usage code, we can treat it almost like a pointer. In an if statement, we can compare it, and when we actually know we have a value, we can dereference it using the star operator. Again, I'm sure this is familiar. It's just worth a review. And that gives us a lot of what we wanted. And it is nice, simple, clean code. But doesn't give us the ability to distinguish the different error types, the extra rich information that we wanted the enum for, or the exceptions for. Has another problem we'll come on to in a bit as well. But that's still optional in C++ 17. Let's really bring it up to date then. So C++ 23, we now have stood expected. So this is the type that I talked about in my previous talks as being off in the future, now in C++ 23. So I don't know if anybody's actually using C++ 23 features yet, but we should certainly start, I see a few hands going up, certainly start learning about these. So it's a good opportunity. How does it work? Very much like stood optional, except we have the ability to provide a second type, which is going to be the error type for error handling, or the unexpected type, more generally. And the only more complex bit really is in the return. We have to return a stood unexpected of our error type, just to make sure that we can distinguish it and it overloads correctly. And the actual error type does need to be the same type this time. So here I'm using an exception type, just to show you can do that. It's maybe not the best thing to do, probably some sort of error code. But if you did use an exception type, it has to be the same one. So we couldn't return stood runtime error for one and stood domain error for another. So it's not like exceptions in that sense. It has to be the same type. So here I'm just using the string to distinguish them. And in the usage code, almost identical to optional. We use the if statement to check whether it holds a value or not. If it does, we can dereference as before. It's only in the error case. Now we just have .error, and we get an error type. Nice and simple. If you've ever tried to use std variant to do something like this, you know it's a lot more work. So this is a big win. And although there's a lot more code here, it's pretty simple, understandable code, even if you haven't seen std expected before. So I like std expected. But I alluded to a problem with optional, and it's a problem with expected as well, so let's deal with that at the same time. In this case, we've only got one call to a function that returns std expected, and we deal with it straight away. But often we want to compose bits of code together that have different stages of error handling along the way. They might be in separate functions, or it might be all in line like this. Typically, when you see examples calling out to separate functions, I thought it might be nice to use a more in-line example this time. This gets a little bit more messy, as you can see. So I did warn you some of the code's going to be a bit small, but we can zoom in on this a bit. Hopefully you can read that. Let's walk through it, because if you're not familiar with std expected, this may be take a little bit of reading. So really we start on that third line, where we call parseInt in the if statement. But we've got to pre-declare another std expected, because at some point we're going to change the value type. And we're going to have to do that inside an if statement and then refer to it outside. That's why that's there. So if we do get an integer, then we can dereference it on the fourth line, subtract 1 from it. Now we've got another integer. And then the last thing we want to do is divide it into 1. So 1 divided by our integer, which means if our integer is a 0 at this point, we want to guard against divide by 0. So that's where our second std expected comes in. So we've got std unexpected divide by 0. But notice at this point we're dealing with our new expected, the one that takes a float and a runtime error. And that means that if we didn't get an int when we called parseInt right at the start, we drop down to that else right in the middle. You can see how the control flow is jumping around. And we've got the error, but now we need to convert it into a different std expected with the same error. Because now we've got to deal with the same type, the one that's std expected a float instead of runtime error. But now we've got our final std expected. We can do our normal check at the end, if statement, dereference, or .error. So it's not too complicated, but it's not that nice, really. Is this really the best we can do? Oh, and here's the output. Well, we did actually get where we wanted. One thing we might want to do, because one problem here is the happy path ends up in the middle. And we get all this extra nesting. We have a few more levels. It starts to emerge what we sometimes call the arrow of doom. We're sort of pointing to the happy path in the middle. If we invert the ifs, we get the happy path ending up at the end. Maybe that's a little bit better. It's still going to be indented. You decide. Might be slightly better, but it's fundamentally the same code. Now, that bit where we got the uninitialized std expected at the top and assignments in the middle, in my opinion, you should always consider that the code smell. And there are ways to avoid that. And the main way that we address that these days is with the immediately invoked lambda expression. Hopefully, most of you have seen this at this point, but if not, I'll walk you through it anyway. So we start a lambda expression at the top, and you can see at the bottom, or the last highlighted line, we're immediately invoking it. So we end up with the value that it returns, not the lambda. And within the lambda, now because we're in a function-like thing, we can return out of it. We don't need to use assignments anymore. So we can return our new std expected, or we can return the one that we've had to convert the error across. We still have to do that manual propagation, unfortunately. But it is better, because we lose that need to have an uninitialized variable and then mutate it. You can see we initialize at the top. We can use type inference. We can make it const if we wanted, because this is a slide where I've omitted a lot of consts and things like that, but you can do that there. So that is nicer. In fact, this isn't too bad, really, considering the alternatives. It's not too bad. But can we do better? And I wouldn't be asking that question if not. So another C++23 feature, which applies to both expected and optional, is the so-called monadic operations. And again, this is something I've talked about before, but it has changed a bit. So let's have a look at what they are and how they're going to help. This is how we'd write the same example that we just looked at. So instead of the immediately invoked lambda expression, we're calling a couple of member functions on stood expected. The first one is transform. So transform will, if the expected it's called on has a value, it will invoke the lambda you pass to it with an unwrapped version of that value. So you can see we're getting the integer here, we don't need to dereference anything. So that's a little bit nicer, it's also safer. And then whatever you return, it's going to wrap that back up in a stood expected. Could be the same value type, it could be a different value type. Depends on your needs. So you don't have to do the unwrapping or the wrapping. It just transforms the value. That's where we can do our I-1. So nice and clear on its own line now. Because we've got a new stood expected back, we can follow on with another monadic function. This time it's going to be and then. So and then starts off the same way. If you have a value, if the expected has a value, unwraps it and passes it to the lambda. Now this lambda, instead of returning a value that gets wrapped up, it has to return a full stood expected. Because you may want to do additional error handling, and that's what we want to do here. So if our I is equal to 0, we return our stood unexpected. It's the same error type, same value, but a different value type in this case. And that's why we've had to spell it out as the lambda return value, because we can't infer that we want a stood expected, a float, and stood runtime error. But apart from that, this is actually really nice and clean. We're doing almost the minimum. We don't have to do that manual propagation anymore. That part's done for us. We don't have to do the manual wrapping and unwrapping. All those bits are handled by the machinery, and we just write the bits of code that we actually wanted and sequence them together. So that's actually quite nice. Now, if you're not familiar with this way of doing things, it might look a bit awkward, might actually look more complicated, but once you get used to it, this is simpler, because you're taking away the distracting parts and just focusing on the bits that you need. And just to compare that with what we had before, our best effort, we would put it in an immediately invoked lambda and compare that to this. So, yep, slightly less code, I think, a bit more focus on the bits you're actually interested in. It takes a little while to get used to, but please do try to use these functions. So we looked at two of them. I think I said there were four. If I didn't, I should have done. So we've done transform and then. Now, you might be looking at the bit at the end. We've still got that separate if statement and that final handling where we're printing the result. That's actually usually what you want to do. You want to do all your processing to get a final expected, then see whether it still has a value or not, and act appropriately. But you can move that in as well if you want to. And we can do that this way. So now the happy path ends up on a transform, and the error path ends up on a transform error. You can do this, I wouldn't necessarily recommend it. And the reason why, you can sort of see there, hopefully, we're still having to return something, because we're still trying to produce new stood expecteds. This is a composition for data processing, not for side effects, but you can do them there. So this is a little bit of an abuse of the system, but you can do it. So do have like a final section where you test whether it has a value or not and take appropriate action. But that does introduce you to transform error, the third of our monadic operations. For transform error, if the stood expected has an error rather than a value, unwraps that and passes it to its lambda argument, and then takes the result, which may be a new error, and wraps that back up as a stood unexpected. So it's just transforming the error part. Again, it could be a new type. So that's quite useful, perhaps not quite so much for this. We'll see it again in a moment. And the final function, I'll throw that one in now as well, is or else. So or else takes, again, a lambda which takes an error type. So it's not shown here because I'm not quite using it here, but take the error type and then you can return a whole new stood expected. So you could change the value or the error, and you usually want to return a new value. That's what we're doing here. In other languages, you may have seen things like a null coalescing operator. That's basically what this is doing. It's saying, keep going, if you don't have something at the end, use this value instead. That's really the primary use case for or else. Now, optional already had value or, which seems to do the same thing. But the difference here is that value or takes an actual concrete value to use as its default, which if it's something that's expensive to compute for some reason, that can be an overhead that you don't have to pay for. So or else, it's lazy because it's taking a lambda. So it's only going to execute the lambda if it doesn't have a value, if it only has an error. So that's useful as well. But you still need to unwrap it at the end, because it could still be an error. Okay, I'm just going to go back and show you another example of transform error, because our previous one was a little bit of an abuse. So this time, I'm taking an actual error type. It's deduced, but it's going to be our stood runtime error. And I'm unwrapping the string from the exception type, x.what, and just returning a stood string instead. So we're transforming the error type to the underlying string message. So at the end, you can see now, although you can't really see the types because it's all type inference, our final expected type is actually an expected of float and stood string. And the first one was an expected of int and stood runtime error. So we don't need to do the .what in that final usage code. So they are the 4 monadic operations that stood expected supports in C++23. It's worth learning them. So here's a handy summary chart. And stood optional also supports the first 3. Doesn't support transform error because it doesn't have an error type, so that part's obvious. And the and then, it obviously doesn't support a stood expected return type to stood optional. But and then takes a lambda, which takes a value, and returns the stood expected of some value type, some error type. Transform takes a function or a lambda, which takes a value and returns a value, which gets rewrapped. Or else takes a function or lambda, which takes an error and returns a value. And transform error takes a function or lambda, which takes an error and returns an error. So, might be worth having this chart handy until you get used to it. Well, once you do, it's actually quite straightforward. So that is the new error handling features in C++23. Stood expected, and the monadic operations on stood expected and stood optional. Very useful. Hope you'll agree. But that's not the end of this talk. In fact, we are just about halfway through. So let's go to part 2. And I'll walk over this side, because why not? So what's part 2 about? Let's see what our robot says. We are going to use a different example for this one. Again, an evolution of the same example throughout. Instead of passing a string into an integer, we're going to go the other way around this time. We're going to take an integer and return a string. And specifically, as the name suggests, we're going to interpret it as a month number, month as string. And this is the implementation we're going to use. Lots of different ways we could do this. This is one of them. So we've got just a raw array of strings, English, 3-letter abbreviations for the months. And we're just going to index into that. We're doing -1 because month is going to be 1-based, number between 1 and 12. And we want to make that 0-based. But that's it. Nice, simple, straightforward, perfectly valid way to do it. Obviously, you can see immediately it has some problems. See some nods. But yeah, what happens if we call that? So we can call it with a valid month number and a couple of invalid month numbers. On my machine, I got this. So the valid month number converted fine. For 0, I got nothing. And for 10,000, I got some garbage memory. Of course, that's completely undefined behavior. It can do anything, including reformatting your hard drive. Has anybody ever had their hard drive reformatted because of undefined behavior? No, I didn't think so, but it could happen. So we're told. But lots of bad things can happen. We definitely don't want to invoke undefined behavior. So what do we do? One thing we can do is just make this into a disappointment. So we're going to have a wide contract, a complete function. So we just bounds check and throw an exception. And that's a perfectly valid way of handling this. In fact, it's the default way that most other languages would approach this problem. But we're C++. We know better, of course. And we might say, but actually, I know that I've got a valid month number here because I've already verified it somewhere else. So why should I pay the cost of checking again and then having to do exception handling? Just keep it simple. And so we'll probably put an assert there, so we can at least catch that if we encounter it during development. And now, if we do call that, we're going to have to do some external checking. If we have unvalidated data that we've got from somewhere else, maybe we read it from a file, got it from a user, across the internet, wherever it's come from, even some other untrusted piece of code, something outside of our control, no guarantees, we're going to have to check it. And now we've got that same bounds check duplicated inside the implementation and outside the implementation. And that's probably not a good idea, especially as it can get out of sync. And then we're back in that undefined behavior land. So we don't really want to do this, but we don't want to pay that cost either. So this is where we start to get into not necessarily my unique ideas, but things that I do that not everybody does. But I like to have 2 versions of this function. The original one that has the assertion, which is really a precondition, and one that I usually use the underscore checked suffix, so month is checked in this case, and that's going to use one of the disappointment approaches that we discussed in the first half. So it could be exceptions. Here I'm using stood expected because we just introduced that. We'll do our check there. And if it passes the check, we can forward on to the first function. So if we're doing more complicated work, we're not duplicating that. And now we can choose at the call site what type of error handling we want to opt into. Do we know we've got a valid month? We want to call the lower level version? Or we're not quite sure we want to call the checked version. So we've got that choice again. So that's good. You might prefer, as indeed I do, to switch that round. So the default is the checked version, and you opt in to the low-level, more dangerous version with the undefined behavior. Now, I know some people prefer it the other way around. I prefer it this way around. Make your own choice. Somebody pointing out a problem? Sorry? The
month is string. The last one should be month is string unchecked. Otherwise, you'll have infinite recursion.
Oh, yeah, well done, thank you. I just saved this slideware, so there is a bug on the slide. That should be month as string unchecked at the end of the month as string function. Good catch, I'll fix that. Okay, so even my slides have undefined behavior. All right, so this was using stood expected. That does mean that this has a different signature between the 2 functions, and that may be fine. But if we used exceptions instead, one side effect of that, if you pardon the pun, is we've got the same signature. They're both taking an integer and returning a string. The reason that is significant is you could try a different approach. And this is a little bit more novel, but it does work. So I'm going to introduce an enum to say whether we are in checking mode or non-checking mode. And we make the function a template, templated on that enum. And we can default it, so we can make the default strategy checked here. And inside the function, we can use if const expr to check that enum. So it all happens at compile time. And if we are checked, we do the runtime check, throw an exception. Otherwise, we carry on, we do the assertion anyway, and we've only got a single function with a single implementation, everything in one place. Reduce duplication again, and achieve the same result. And in the example code here, we're calling it without a template argument, so we're just getting the checked version. And if we called it with unchecked, we would get the assertion behavior. So I think that's quite nice. I haven't road tested this too much yet, so I'll be interested if anybody else has done something similar. But I think it's a promising approach. Might want to take it even further. There is still a little bit of duplication here. So we've got the call to isValidMonth twice still, although we separated it out into a function, separate function, we're calling it twice. If you can tolerate a macro, you could roll that up into a macro, call this assert or throw. And now because we're only passing that condition in once for both uses, I don't even need a separate function anymore. So that could be something you could do. You could do it without a macro as well. It's just slightly uglier or slightly less performant. But maybe somebody can come up with a better way to do it. So that's something you might want to do. So far, so good. Got the options, we've got the safety where we need it, we've got the performance where we need that. But really the problem here is we've got this difference between, in this case, the integer. The range of the integer, about 4 billion different values, I think. Only 12 of them are valid. That's the domain of the function. That's the difference that's causing us the problem. Not all contracts are like this, but this one is. There's other ways to deal with that, which may actually be better. And I prefer, where possible, to use correct by construction techniques. Some of you may have heard of this and tried to use it as well. How does that apply in this case? In this case, it's going to amount to writing a dedicated type for handling month. You may use a third-party library for bounded integers or something like that as well. It's another approach. There's some benefits to doing this a little bit more custom. However you do it, you're deferring the validation of that range of the integer to the constructor of this type. So in this case, the constructor is checking whether it's valid and throwing an exception. If not, whatever you do, when you come out of that constructor, you know you've got a valid month number. We don't have to check it anymore. So our month is string. We can now take a month type. It doesn't have to worry about it anymore. It's checked once, and we can push that check right back to where we were getting our unvalidated data from. And after that point, use our month type. We never have to check again. We can rely on it. So that's pretty good. And the usage code, as you would expect, looks much like this. So that was using an exception. But what if you still want to construct a month type from a value you know is a valid month? Well, you just add another constructor. We can't overload constructors. Can't give constructors different names, but we can overload them. So this is one technique using a tag type. So you can see at the top I've got this struct unchecked, completely empty. Only purpose is to provide an overload for our second constructor. And there's no real overhead to that because that just gets optimized out. So if you haven't seen that approach before, that's like a tagged dispatch. Useful in this case. And if we do have a month type, you might even want to move our asString function in there as a member function anyway. That depends on your use case, but has some nice side effects like that. So that's just an example of correct by construction, which I think is really useful for tackling these sorts of problems where you want to really control and manage that checking, whether it's a runtime disappointment like check or or a more static contract check, but push it back to the point that you get unvalidated data. And after that point, you use a guaranteed value. Okay, so far so good. I've talked about contracts a bit as a general concept. We said that asserts can act, in this case, like a precondition, which is a good start. I did say we're going to look a little bit ahead at an upcoming language feature. I say upcoming, it was in C++20, got taken out before we finished the standard. We're now on the C++26 map, and contracts is just about on track, last I heard, but it's about 50-50 if it's going to get in. So it may even be a C++29 feature. So I don't want to overpromise, but I'm hopeful at some point we will get contracts as a language feature. Now, this is not going to be a deep dive on contracts. As I said, there's other talks dedicated to that. But I just want to see how it fits into this particular problem, and also what other problems it might present. So we're going to do a bit of a fake contract. So you can see pre here. That's the keyword that's currently in the contracts proposal for a precondition. And it's playing exactly the same role that our assert was before. It looks almost identical. But it does have some interesting properties. So if we call this now, and by the way, I've gone back to the simple function just to save some screen space. And if we call that, and I noticed I got the calling code the wrong way around. It should be test1 first, but ignore that. Slideware. For our valid date, we get that date back. For the invalid date, we actually get a lot more information than we got from the assertion, although that was platform independent. But this is no longer platform dependent. This is actually defined. So it tells us that the precondition failed, so it's a bit more expressive. It tells us the expression that failed, file, 9-number function, and then it aborts. So a bit more information, but very much like the assert so far. Where's all that information coming from? So I said this is a fake contract because we don't have the language feature yet, so I just knocked up this slideware version. So we've got a macro, pre, and you can see it's just got an if in there, as you might expect. But here's the difference, here's the key. In the failure case, it calls a violation handler. So it's deferring how to handle that failure to something else. It passes in the expression. So what's the violation handler? Again, this is my hacked together slideware version. Not what it actually looks like in the paper, but gives you an idea. So right at the bottom there, you can see violation handler is actually a function pointer. By default, points to default violation handler, which is just above. And the default violation handler, that's what's giving us that result. It's just printing a message that it's making up and then aborting. The message is coming from the violation info at the top, which was just a way of packaging together the expression and a source location and then being able to print it out. So nothing terribly complicated. But this is basically the flow. We call violation handler, which is a function pointer to do the actual behavior. Because it's a function pointer, we can replace it with our own function violation handler. And we could replace it with, for example, a throwing violation handler. And the throwing violation handler just throws an exception. And this time we'll make it a logic error, because that's what we're dealing with. We can still use our make message as before, so we get the same output effectively. If we call that, and now we can treat it with exception handling. So we get the same message, but we don't abort. We can carry on. This can be recoverable. That's an interesting property, because we've taken something that was a narrow contract and converted it into a wide contract or a total function, which is interesting and has some sometimes annoying properties, actually. For example, if we just look at our month-for-string function, and especially if we change our return value, we'll make it a string view instead, because we know from our implementation we've already got a global array of strings, so that should be safe. there's nothing in here that should throw, at least with the default violation handler. Which means you might be tempted to put no except on there. Maybe you have a good reason to, or maybe you just think it should be no except because it doesn't throw. But then you've got that problem because pre may throw if you substitute the violation handler. Now this particularly is a problem if you want to test your contracts. So I say this function has a contract, I want to test that it actually detects that. So you might say install a throwing violation handler, which I didn't show here, but assume that's been done. Call my contract function with the contract and check that it actually threw something, which of course doesn't work if you've got no except there because it's going to block that exception and it's going to abort anyway. So take it off and that actually works. So it's quite a nice way of being able to test contracts by changing substituting the violation handler. And for some of you, this may be familiar as what we call the Lakos rule, at least applied to the standard library. So the Lakos rule has been part of the standard committee's view of things since C++11, when the no except keyword was first introduced, to the point that no functions that have contracts, narrow contracts in them, in the standard library, are allowed to have no except, for this reason, because they want to be testable. So that's been around as an idea since C++11, but last year, John Lakos, for whom this is named, wrote a paper on it. It's quite a big one, actually. You think, actually, we can describe that in a paragraph or two. But no, it goes into real depth. It's not just about testing. There's a lot of extra consideration. I recommend you read the paper, because it's not a proposal for a language feature. It's a proposal for handling contracts. And as we get contracts in the future, this is going to be important. I think we can sum it up, though. I'll pull out this quote from the paper. Just to give you an idea. So he says, absent a vanishingly rare and compelling engineering reason to do otherwise, deviating from the Lakos rule is invariably and absolutely a terribly bad idea, especially within the C++ standard library specification. So he doesn't mince words. And if you read the paper, you can see why. And particularly applying to the standard library, but as a general principle, it applies. So familiarize yourself with the Lakos rule. I'm not maybe quite as strong about it as John is, but I think there are some cases where we might want to work around it. So here's my recommendations for working with or around the Lakos rule, particularly for testing, at least. The number one is basically follow the Lakos rule. So don't use no except if you have preconditions and you want to be able to test your contracts. But if you have a valid reason for needing no except there, make sure you do. If you do have a valid reason for it, a couple of things you can do, or a few things. If you have a simple precondition, like the one we've been dealing with our month of strings, just a one-line bounds check, nice and straightforward, but separated out into its own helper function. Well, maybe just test the helper function and sort of rely on the fact that that's what's being used in your actual function. It's not quite as strong because now the function could do something different at some point in the future, but that may be one way that you can actually get your test in and the no except. The next one is maybe one of those approaches I showed earlier where we can have two functions, the checked and the unchecked version, or a single function that's a template with a policy on it, like the checked, no checked version. Now we can use the checked version to test our contract enforcement. It's very similar to the replacing the violation handler, but it's specific to a function now. But that relies on you writing it that way in the first place. Some slightly more iffy recommendations, I wouldn't even call them recommendations, but there are things you can do. One is, rather than using no except concretely, use a macro that now you can conditionally compile to no except on or nothing. And that means you're then going to have a special build for testing purposes. And I don't usually recommend that, but it can be something you can do if none of the options work for you. And finally, if you have a test framework that supports dev tests, and I know Google Test does, Catch2 doesn't, unfortunately. I think Google Test is one of the few that does. This can help. So a dev test will fork the process, and then the monitoring process will watch the forked version, make sure that it actually terminates with an abort, i.e. it called the contract. Which sounds like, oh, that's great, that solves the problem. Except that it's really slow. Might be okay for one or two, maybe a dozen, and if that's what you've got, that can work for you. But if you've got hundreds or thousands of these, maybe even millions, it's just not going to be workable, at least not in a unit test context. Maybe you want to run it occasionally on a build server. That could still be an option. But weigh these all up and see what makes sense for you. But generally, just follow the Lakos rule and you should be fine. So, covered quite a lot. Let's try to summarize it. So we really looked at two areas: disappointments, runtime error checking for things that are predictable. And we looked at quite a few different approaches. Some old and familiar, some new, some novel. But we also contrasted that with logic errors, where we don't want to handle them in the same way as disappointments most of the time. If we're in a state that we don't expect to be in, then there's all sorts of guarantees that may be off. So best to just stop whatever we're doing, usually just completely aborting, and that's why we use the assert. But sometimes we don't know at the implementation level whether this is going to be a disappointment or a logic error. And so approaches that allow us to defer that decision to the caller can be really useful. And so that's why we looked at the checked unchecked versions, the policy-based checking, and correct by construction techniques. And finally, we just looked at preconditions specifically, talked about throwing violation handlers and the Lakos rule and avoiding no except in that particular situation. So a lot of ground, but hopefully all makes sense and all hangs together. But that is the end of the talk. So it just remains for me to say thank you. And do we have any questions? You want to come up to the mics?
Hi, great talk. When you had your month example, you kind of had that strong type wrapping that. One thing I've thought about is doing kind of something generic where you might have a ranged int or something like that. It would be a template and it would take non-type template parameters of int that would then give the range for it to be more flexible type. Have you ever thought about anything like that?
Sorry, I'm struggling to hear you over the AC a little bit.
Sure,
from this
yeah.
position. Can you repeat that?
So let's say it was called ranged int would be the class, and it would have two template parameters that were ints, and one would be the min, one would be the max. And so when you would create that, when you created the constructor, it would check that condition and throw an exception based on that case. So it's more flexible than month. You could use that anywhere you needed a range type in, so you wouldn't, if you had already checked it above, you wouldn't have to check it again when you passed it.
Right. Yeah, there's variations on pretty much everything that I talked about, particularly when it comes to checking contracts, different approaches. And also, I kept to some very simple examples because we only had so much time. It does get more complicated and sometimes more flexible. So yeah, that sounds reasonable. Thank you.
Hi, I have a question about the Monadic Operations. I find I really do want to use these, but because I'm working in an existing environment, I have things that take multiple input parameters, which makes them a little...
Sorry, struggling to hear you again.
Yeah, I have functions that take multiple input parameters, which makes them look a little worse.
Yeah.
I do have side effects a lot, and I'm wondering, like, should I adapt my functions to take a single input parameter to enable these? Am I just trying to use them in the wrong place? Do you have any kind of guidance there?
Yeah, can just take a little practice to get a feel for what's appropriate or not. But generally, when you start using terms like side effects, we have to really quantify whether the side effect is really the effect. Is that the main purpose of calling it, like, std print? The effect is the main thing. Or is it just something that does it along the way, like logging something, but really it's just computing a result? So if the main purpose is producing a new result, then using it as part of a data flow is quite appropriate and works nicely. If the effect is the main thing, then that's probably not a good use of the monadic functions. But you can sort of go in and out, you can do a few monadic operations, and then just have a simple if, carry on, and then maybe do some more monadic operations. So you can mix and match. But yeah, that's generally the distinction.
Okay, thank you.
No problem.
Hey, I noticed that you used std runtime error as the sort of error in expected. I guess from talks long ago, I saw error code.
Yes.
And that sort of stuff. What are your thoughts on using error code in the error part of expected?
So you're talking about
guidance on doing so? Yeah,
you're talking about std error code specifically. Yeah. In fact, that's what I did in my previous talk, Dawn of a New Era, where I talked a lot about error code. So you can still go back and watch that part. Error code is a very useful type. We've had it since C++11, but who is actually familiar with std error code? Yeah. Handful of hands. It's a bit of a mixed metaphor. Yeah, not many people are that familiar with it, but it's actually really useful. So it's essentially a big enum for all the POSIX error codes, but more generally, it's a way of producing your own enums or integers representing error codes and being able to map between them. So you can compare something from your error domain with, say, the POSIX error domain. So anything that vaguely resembles the POSIX error domain, std error code is actually a really good approach to doing it. Has some little shortcomings, which I talked about in my previous talk, but generally, yeah, that's a really good type to use with std expected, or just an enum. And I did consider going back and changing my slides to use that instead, because I thought maybe the exception is distracting, but I didn't have time in the end. Yeah, a simple value type is what works best with std expected, and that may be std error code. So, good recommendation. Thank you.
Hi, thank you for the talk.
Welcome.
In one of the talks before, I've heard about the concept of cooperative error handling, when your function returns not just an error, but maybe some options to proceed in this case, such that the caller can choose between them. Have you heard about this or think about it?
Not off the top of my head. It sounds interesting. Maybe we can talk about that more afterwards. Not sure we can have that discussion now. I've got 2 minutes left, but yeah, I don't think I have a particular opinion on that at this point. Thank you.
Hi, thank you for the talk.
Welcome.
When you were introducing the monadic operations, you have a transform. There's one thing which I was missing. You can also explain never nester. So you can say if, fail, and then you can reduce your else case. That will be more cleaner code.
Oh, if you only need to handle the error case.
Yes.
Yeah, you can say if. Well, you can do the, I forget what it's called now, initialize statement.
Means you don't need to write both if and else. You can say if error, early fail, else you don't need to write. You can directly go to the normal code.
Yeah, you can do it just with the if, but I think you need the initializer statement with the semicolon in the middle.
Yes, but you don't need else case. So it will be more cleaner.
Yeah, if you don't need to handle it, I agree.
Thank you.
Yeah, thank you.
Hello, thanks for talk.
Welcome.
The core guidelines mentions a technique of using a pair or tuple to return a value in error code and structured binding to separate them out.
Okay.
I haven't been fortunate enough to use newer standards of C++, so maybe that's being replaced by some of these techniques, but what do you think about it mentioning that technique for those who can't use exceptions?
Yeah, so if I got you right, you're talking about returning a pair or a tuple. So whereas std expected is either a value or an error, the pair or tuple would be both, but only one of them would be valid, or one would be the signal to say that the other is valid. which works and has some advantages. As you say, you can use that with structured bindings. But I'm not sure that's better than using stood expected, because stood expected is pretty fine-tuned for error handling cases. And it's got now, particularly with the Monadic Operations and some other support, fairly clean support for it. But it is still a valid approach. I'm not sure there's a particular advantage to it. There's also some overhead because it's got to carry more data some of the time. But if you see there's a particular advantage to it over using stood expected, that will be interesting. Thank you. So I think we are at time anyway, so perfect timing. Well done, everyone. Thank you again.